Hello and welcome to this video on using matrices to express linear transformations. So what we're going to see in this video, I'm first going to define a matrix transformation, right? And what the standard matrix for a transformation is. I'll go over several examples of turning a transformation into a matrix transformation. And then I'm going to talk about, in the latter half of the video, how all of the matrix transformations you come across are actually linear transformations, and vice versa. Every linear transformation we'd ever come across is also one of these matrix transformations. Pardon me. And then I'll go over the last part of the video with examples where I'm given a transformation and asked if it is a matrix transformation or not, which is kind of like a previous video where basically, if I'm given a transformation and asked if it is a linear transformation or not, that'll be equivalent to asking if it is a matrix transformation as well. Okay. So the first page is defining what these matrix transformations are. So a transformation, again, it could be called T or whatever you want, but usually in official like theorems and notes and writings and definitions, it's called T for transformation. A transformation T from Rn to Rm, right, domain codomain, that can be written or can be defined as T of x equals A times x, where A is an m by n matrix, is called a matrix transformation. So what this means is that any transformation where you can express the output, right, the T of x, where you can express the output as a matrix product, right, like a matrix A multiplied by the vector, the input vector x. If you can express it that way, then you do have what's called a matrix transformation. And then this matrix A, right, the matrix A that defines the transformation T, is called the standard matrix for that transformation, right? Standard matrix for T. Okay. Now you're going to see some transformations can be written this way, right? Those are matrix transformations. And you'll also notice later in the video that these transformations that can be written this way are also linear transformations. And then the ones that can't be written this way as a matrix times the input, you'll see that those are non-linear transformations. Okay, so non-linear transformations won't be able to express as these, written as these matrix transformations. Okay. So my first example. So here I have a transformation, actually an operator, because my domain and codomain are the same. I have this operator called T from R2 to R2, right? And this is the way the rule is defined. So my input is some vector from R2, right? Some vector with two components, x1 and x2. And my output is also a vector with two components, right? It's from R2. And the first component is x1 minus x2, right? The first component of the input minus the second component of the input makes the first component of the output. And the second component of the output is the first component of the input plus twice the second component of the input. Now the question is T a matrix transformation? All right, so I'll write that out. And another way you could ask this, all right, that's equivalent to asking this question. Can we express the output? Can we express the output, which, the output here is x1 minus x2, and then, second component x1 plus 2x2, as a matrix A, right, some matrix A, multiplied by the original input vector. Right, can we express this as a matrix times the original input vector? All right, you can see here that the answer would be yes. If you take a look at this, all right, they're lined up nicely. Where I have the terms with x1 lined up, terms with x2 in these components are lined up, and you've seen this done in systems of linear equations before, where you have your equations involving the variables on one side and constants on the other, and you could take those equations involving variables in a system and write it as a matrix product, where the matrix here, down the first column, I'm putting the coefficients of x1, right, 1x1, 1x1. And then down the second column of this matrix, I'm putting the coefficients of x2, which would be negative 1x2 in the first component, positive 2x2 in the second component. And there we go. Those are all the coefficients of all the variables that I'm seeing. And you see how this is a 2 by 2 matrix here. And this matrix multiplied by the original input vector, right, the x1, x2 input vector, would be equal to this. And you can test it out. A 2 by 2 times a 2 by 1 would give me this 2 by 1 up here, where you see the first row, first column would be 1x1 minus 1x2, x1 minus x2. And then the second row, first column is, this 1, 2 matrix product with x1, x2, 1x1 plus 2x2. Got it. So yes. Yes. So yes, T is a matrix transformation. And like I said, later we're going to see that this is equivalent to telling me that T is a linear transformation. Right? If you recall, I'll bring up those what makes a transformation linear again later in the video. All right, and this 2 by 2 matrix, which I'll write again here. This is called the standard matrix for T, right, for this transformation. Okay. And so now, if you were asked to say find the image of a certain input, now you can use either way the output is written. All right, you can use it the way it was originally written to find the output, or as this matrix product. So let me show you. All right, so same transformation here. So let's say now I'm asked to find the image of the vector, 2, 3 or something. Right, find T of 2, 3. Now, like I said, you can do this a couple ways now that we know this is a matrix transformation. One way to do this would be just, replace x1 with this, x2 with that, and we'd have 2 minus 3 for the first component, or, negative 1. And 2 plus 2 times 3, or 8, right? 2 plus 6. So this negative 1, 8, right, is the image of the vector 2, 3 under this transformation. But now, since we know that this is a matrix transformation, I can write my output as a matrix product. We could also do it this way. If I said what's t, the value, the image of the vector 2, 3. I go back and remember we can write our outputs. We can write our output this way as this standard matrix, right, this 2 by 2 matrix here, multiplied by the input vector. So I do that here: 1, -1, 1, 2, multiplied by then again the input vector is 2, 3. And this is a 2 by 2 times a 2 by 1. That would result in a 2 by 1, right? So something with two components, a vector from R2, like I need to, right? The output should be in R2. First row, first column is 1 times 2 minus 1 times 3. So 2 minus 3, -1. So far, so good. Right? These better be the same. Then the second row, first column is 1 times 2 plus 2 times 3. That's 2 plus 6, or 8. And you get the same result, right? So you don't really need to do both, but I'm just saying that now that we know this particular transformation is a matrix transformation, you could express every output as a matrix product, right? With that standard matrix times the vector that's being input times the input vector. Okay, and that's just one example, right? You could do this with any input vector, and whatever you input, you're always multiplying by this standard matrix, the 1, -1, 1, 2 here to get the output. Okay, so let's keep going with this. More examples. All right, so here's another one with that's going to have a 2 by 2 matrix. It's R2 to R2 again. All right, so this time, again, my input vector has two components, x1, x2. My output vector has two components, right? It's from R2, 2x1 and 3x2. So again, let's see, can we write this, t of x1, x2 here? Can we write this as just a matrix times the vector x1, x2, or a matrix times my input vector, the way it looks? Well, as I said, let's take a look at what the output is now. That's 2x1 and then 3x2. And then just as I did before, I'm gonna say, hey, every single term I'm seeing has a single variable, and that's really key. Every term in your outputs has a single variable attached. I should be able to write this as a matrix equation. Again, it'll be a 2 by 2. And when I say it should be a 2 by 2, and we'll see this in later videos when I look at transformations between generic vector spaces, not just Euclidean vector spaces like I have here. You'll see that the dimension of the size of the standard matrix, the number of rows, is going to be equal to the dimension of the codomain. Pardon me. Alright, so this is R2, the codomain here, right? That's 2 for the number of rows in the standard matrix. And the number of columns in the standard matrix, you're going to notice, is the same as the dimension of the domain. So I'll just write that up here. And this is going to be true for later when we see transformations between any vector spaces that can be written as a matrix product. That is a matrix transformation. Alright, so I'm setting up this 2 by 2 matrix where my two input variables are x1 and x2. So down the first column, I'm putting the coefficients of x1 in these components. That's 2 in the first component, 2x1, and then you see how there's no x1 down here? So technically there's 0 x1. So my first column is 2, 0, the coefficients of x1 going down those components. And then the second column will be the coefficients of the second variable, x2. So notice on the first component there are no x2s, so 0. and then the second component has 3x2. So this is the matrix, the standard matrix, and then this matrix multiplied by the input vector will give me the input that they asked for here, the same input that's being described. So yes, it looks to me, yes, T is a matrix transformation. Because I can express the output as a matrix times the input vector. Right? And like I said, I'm going to repeat myself a lot. You've probably noticed me doing that in a lot of videos. Saying that a transformation is a matrix transformation is akin to saying that it is a linear transformation. So this would also be a linear transformation. And then again, just one swift example of an image here. Suppose I wanted to find the image of the vector, 4, -3 or something, right? Something from R2. Now, you could go to the way it originally looked, right? That's just 2 times 4, so 8 for the first component, and then 3 times -3, that's -9 for the second component. Oops, sorry, I didn't mean to put parentheses there, that's a bracket. But this should also be the same as our standard matrix, right? 2, 0, 0, 3, multiplied by the input vector, 4, -3. And double check that, right? See how it would be 2 times 4 plus 0 times -3, that'd be 8 for the first row, first column. And then 0 times 4 plus 3 times -3, that's -9, right, for the second row, first column. So that works out, right? And one more time, right, this matrix here that I found, right, this 2 by 2 matrix, that's called the standard matrix for this transformation. Okay. Right. So just, again, a couple more of these. Now I'm gonna just kind of jump. I'm gonna do these a little faster, because and maybe I'll write this time too. If you look in, if you look inside the output, right, so this time the transformation is from R2 to R3. So my input is a vector with 2 components. My output will be a vector with 3 components. And what you're going to see is that the standard matrix for this transformation will be a 3 by 2 matrix, the dimension of the codomain by the dimension of the domain. So T of xy here, right, something from R2 equals, and then something from R3 as the output, x minus y, x plus 2y, -5y. And something I've noticed in the first 2 examples, and something I'll point out here, I'll actually write it out this time. I said it last time. Each term in each component has a single variable. Right, a single variable factor. And that's something we noticed too in the an earlier video I put out. If you've been following, if you've been watching mine, in an earlier video I put out on determining whether a transformation is a linear transformation. If every term in the components, and this is between Euclidean spaces, if it's not Euclidean spaces, then you would just look at the coordinates, and we'll get to that later videos. But if you look at every term here, x, -y, x, 2y, -5y, and each of the components, each one of them has a single variable factor that says just x, just y, just x, just y, just y. Right? That's a good indication that you have a linear transformation. And if you have a linear transformation, you also have one of these matrix transformations. Alright, so I'm just going to write what the matrix product looks like here. So T of xy is going to be equal to some matrix, and as I mentioned, it's going to be a 3 by 2 matrix. 3 by 2. Where down the first column goes the coefficients of the first variable in the input. So down the first column goes the coefficients of x. So you see 1x, 1x, 0x. And then down the second column goes the coefficients of the second input variable, y. Negative 1y in the first component, positive 2y in the second, and then negative 5y in the third. And there's the standard matrix, and it's getting multiplied by the input vector. All right, so yes, again, I can write transformation T is a matrix transformation. I can write the output as a matrix multiplied by the input vector. Right? The input vector doesn't change here. All right, and then again, one box this is maybe let's do this. This 3 by 2 matrix here is again called the standard matrix for this particular transformation. Okay. All right. So then again, you can plug in any R2 vector you wish, and either use this to find the output, or take this matrix times your input vector and get the output. The same result. I'm not going to do an example there. Okay. Then I've got one more of these, and we'll talk about some properties of matrix transformations in a second. All right, so one more here. So T is a transformation, this time from R4 to R2. So I'm taking a vector with 4 components as my input, and a vector with 2 components as my output. And I've got input x1, x2, x3, x4. The output, the first component, is x1 plus x2. The second component, 3x3 minus 2x4. Okay. Now, can I write this? Well, let's do it here. Can I write this as a matrix multiplied by this x1, x2, x3, x4 vector? Can I write it as a matrix times the input vector? Well, yes. Again, if I look at all the terms in the components here, each term has a single variable factor. All right, this has x1, this has x2 only, x3 only, x4 only. If you have 2 variables in a term, it's not going to be linear, therefore not a matrix transformation. If you have no variables in a term, right, just a constant, it's not going to be linear, not going to be a matrix transformation. I'm telling you. All right. And looking at the domain and codomain, right, the dimension of the codomain is 2, right, dimension of R2. The dimension of R4 is 4. So we're going to have a 2 by 4 matrix, 2 rows, 4 columns as our standard matrix. So I'll start it off here with the bracket. And just as before, down the first column, the coefficients of the first variable x1. Coefficients, 1x1 in the first component, 0x1 in the second component. Down the second column, the coefficients of x2. So I have 1x2 in the first component, no x2 in the second component. Down the third column, the coefficients of the third variable, x3. There are no x3, 0x3 in the first component, 3x3 in the second component. And then finally, the fourth column, the coefficients of x4. There's 0x4 in the first component and negative 2x4 in the second. So there's the standard matrix for this transformation. And if I multiply this matrix by the input vector, I will get this input that's described up here, this x1, x2, x3, x4 vector. Wonderful. Great. And again, this 2 by 4 matrix called the standard matrix for T. All right. Wonderful. And you could, if I asked what's the image of a certain vector, you just take those numbers, you could plug it in here, or multiply this matrix by whatever whatever numbers I have for my input vector and get the output that way, get the image that way. Okay, so far pretty easy, I hope. Just like when you had systems of equations and we're trying to write systems of equations as a matrix equation, it's very similar to that. All right, so now I'm going to get into some properties of matrix transformations, and one thing I've pointed out, one thing I've said out loud but I haven't written, is this statement here. Matrix transformations are linear transformations. So they satisfy those two properties, that additivity property and that homogeneity property. Or you could also say that they preserve vector addition and preserve scalar multiplication. And again, I put up a video prior to this on determining whether a transformation was linear, right? So we had to show that these two properties held, and we'll see that here with a matrix transformation. And I'm not going to really show this here. I'm just going to tell you, not only is every matrix transformation a linear transformation, but every linear transformation is also going to be a matrix transformation. So they are equivalent, right? So saying one is just the same as saying the other. All right, so I may accidentally go back and forth between those if I'm talking about a linear transformation and I say matrix transformation, or vice versa. Please know that they both mean the same thing. All right, so let me show you. Here on this page I have shown you that a matrix transformation is a linear transformation, satisfies those additivity and homogeneity properties. So if I have a transformation T from Rn to Rm, such that it is a matrix transformation, right? So that means T of x can be written as a matrix times the input vector x, right? A times x, where A is the standard matrix. So suppose I have u and v from Rn from the domain. These represent any vectors from Rn, and R is a scalar, right? Little r here belongs to the reals. That's just a scalar. That's not a vector. See, it satisfies the additivity property, right? If I were to take the sum of u and v first and apply t to it, remember when you apply t to your input vector, that's equivalent to a matrix times that input vector. So this is equal to A times u plus v. And u and v are matrices. They're like they're n by 1 matrices, n by 1 column vectors. And remember, matrices, you can distribute matrix multiplication over addition. So this is equivalent to A times u plus A times v. And A times u would simply be T of u. A times v would simply be T of v. So indeed we have the additivity property for a matrix in a matrix transformation. T of u plus v is equal to T of u plus T of v. So I've checked that there. That's good. And then the homogeneity property holds also. Like the matrix transformations preserve scalar multiplication. So if I took a scalar multiple of u, r times u, and applied t to it, then that would be equivalent to the matrix A times the vector ru. And again, u is a column vector. It is an n by 1 matrix. So I have a matrix here, and a scalar. You may remember that multiplying matrices is associative, and scalar multiplication with a matrix is commutative. So if I multiply these two, it's the same as multiplying A times R first and then times U. And then you could switch the order with scalars. Scalar multiplication of matrices is commutative. So then I could basically have R out here and then R times the vector AU, right? The product AU. And A times U is just T of U. So yes, T of R of U, R times U, is equal to R times T of U. Right? It's got that homogeneity property. It holds for any vectors from the domain and any scalars from the real numbers. Right? So it checks out, thumbs up there, good. Good on both of them. So what I set up here is true, right? A matrix transformation, if you have one, is going to be a linear transformation, satisfy those properties. and again, I haven't shown this, I'm just kind of saying it off to the side, any linear transformation is also going to be a matrix transformation. You'll be able to write the output as a matrix times the input vector. Alright, so now on the next page, I scroll through some properties of matrix transformations, being that they are linear transformations, and you'll notice that two of these I've already shown. So here are some properties of matrix transformations. So again, let T be a transformation from Rn to Rm, and it is a matrix transformation, so I can write T of x as, a matrix A times the input vector x. All right, then for all vectors from the domain, right, u and v from the domain, and scalars, r from the reals, the following four will be true. Okay, all four of these will be true. Now, two of them, really, you can get the first and the fourth from these two. All right, you can get the first and the fourth from these two, from 2 and 3. So one thing is the image of the zero vector in Rn is the zero vector in Rm. Right? So again, the inputs are coming from Rn, and the outputs are coming from Rm. Right? So these are not the same zero vector. Okay, but they still are the zero vector in their respective vector spaces. So in any matrix transformation, the zero vector from the domain will map to the zero vector from the range, from the codomain, sorry. Yeah, don't confuse codomain and range. Then I've mentioned the homogeneity property, the additivity property, and then do you see how number 4 here is really just a combination of 2 and 3? If I apply the transformation t to the difference, u minus v, that's just going to be the same as t of u minus t of v. Right, you can just write u minus v as u plus and then negative 1 times v. All right, then you apply this property and say it's t of u plus t, plus t of negative 1v, and then apply the homogeneity property and pull the negative 1 out. So then you have t of u minus, t of v. So the key properties here are these two. All right. Again, these are the property what make a transformation linear. Those are the key ones. All right. And again, you can actually get the other two, number 1 and number 4, by using these two. And I just showed you how with number 4. For number 1, you could think of the zero vector as a vector u plus the opposite of u in the domain, right? And then you apply the additivity property, so this would be t of u plus t of negative u. Then you apply the homogeneity property, make it t of u minus t of u, and then you get the zero vector in Rn. Right? So these two are the building blocks, the basis for these four. Okay, so in my last several examples in the video, I'm going to be asked, is the following transformation a matrix transformation? Or in other words, is it a linear transformation? Now I could go about it the same way I went with the last video I put up, or whatever it was, a past video I put up on determining if a transformation is linear. So I could check, is the additivity property holding for all vectors in the domain? And then is the homogeneity property holding for all vectors in the domain and all scalars? So you could do that on your own. But another thing I could do is, hey, if this property if one of these properties fails, then you don't have a matrix transformation. So you might say, hey, I noticed that the zero vector in the domain maps to something that's not the zero vector in the codomain. So then you could say right away that is not a matrix transformation or not a linear transformation without having to check the homogeneity and additivity properties. Now be careful. if this is true, that doesn't mean that these are. Right? I didn't say these were equivalent. Right? These are not equivalent statements. Just because one is true doesn't mean that the other three are true. All right? This one could be true, but one of these be false, and all the way around. You could have the third one be true, the additivity property, but it might not be homogeneous. It might not satisfy the homogeneity property. That might be false. So be careful, right? Nowhere on this page did I say that these statements were equivalent. They are not equivalent. Make that perfectly clear. All right. So first example. That's to determine, if the given transformation is a matrix transformation, right? And if it's a matrix transformation, then it's also a linear transformation. Now, right away, I'm noticing that it's not going to be, because look, remember I said earlier, when you're looking at your outputs, does each term have a single variable in it? Well, this term does, right? This has x1 and x1 only. But this one, this is a product. There are two variable factors here, x2 times x3. That's not what I want. All right, that's not. I don't like that. All right. You're going to see that this is not a matrix transformation, or not a linear transformation. All right. Now, remember that first property. Remember I said t of the zero vector in the domain should be equal to the zero vector in the range, or the codomain. Sorry, don't confuse the codomain and the range. Sorry. So let's see. T of, what's the zero vector in the domain? That would be, the vector with 3 zeros, right? It's from R3. And when I plug this in, you'd have a 0 up top, and then x2 times x3, 0 times 0 for the second component. So I get 0, 0. All right, this is working. This works. But be careful. Just because the zero vector in the domain has an image of the zero vector in the codomain, that doesn't mean the transformation is linear or a matrix transformation. That does not mean the transformation is a matrix transformation. All right, so like I was saying earlier, right, those 4 properties I had on the previous page, those are not equivalent statements, right? Just because one is true, right, the number 1 is true, doesn't mean all 4 will be. In fact, I wouldn't even verify that one. All right, if I were you, I would just verify number 2 and 3, the additive property and homogeneity property, because if you can show that it's a linear transformation, then it's a matrix transformation as well. It should be able to be written as the output should be able to be written as a matrix times the input vector. So let's check it out. All right, number 2 was the homogeneity property. All right, 2. So again, for that, let me just make up a here's a random vector, some general vector from the domain. So say vector u is from R3, so it has components u1, u2, u3. So I'm going to let this belongs to the domain, and let little r here be a real number. That's a scalar, right? That just represents any scalar. And now the question is, I guess I should have put a question mark here. Right? Is t of 0 equal to 0? Now, is the value of t at r times u, is that going to be equal to the value of to r times the value of t at u? Right. So let's check that out on the next page here. So what's t of r? Again, you can't start with this. You can't set these equal to each other because you don't know if they're equal or not. So I'm just going to work with one side at a time. Right, so let's say the left side of that equation. What's t of r times u? Right, well, this is where I'm multiplying the scalar by the vector first. So that would be t, and it's standard operations, okay, standard scalar multiplication of vectors in R3. So the vector RU is RU has components RU1, RU2, and RU3. And then I apply, transformation t to it. T of some vector with 3 components. The first component of the new vector, the output, is the same as the first component of the old one, of the input. So I have RU1, and then the second component times the third component for the second component of the output. So RU2 multiplied by RU3. And if I simplify this, you can multiply this. These are all real numbers here, so I can move the factors around. So the output here is R times U1 for the first component, and then R squared times, and then U2, U3 for the second component. All right. Now let's look at the right side of this. That was the left side, T of RU. Look at the right side of this, R times T of U. And see what we get. Now this is where I'm applying the rule for T first to vector U. So if I do that, I'll have R times, and then if I apply T to U1, U2, U3, I'd have U1 as the first component, and then U2 times U3 as the second. And then multiplying this by R, right, doing standard scalar multiplication. This will give me RU1 for the first component. Great, hey, that matches. And then R times U2 times U3 for the second component. That might not be the same. Right, because look, there's R here, but there's R squared in the second component here. So these are not necessarily the same. And I need them to be equal, right? If this is truly a matrix transformation or a linear transformation, I need these to be equal, right? The homogeneity property to hold. All right, so basically if R is not 1, right? If R is not 1 or 0, basically if R is not equal to R squared, this will fail. All right, so let me show you an example of that, and this would be called a counter example. Pardon me. So to show that a general statement is false, right? You just need to show it's false once, right? You just need one example, or a counter example to the statement. So again, just basically if R is not 0 or 1, this is going to fail. So I'm going to let R be equal to 5, and I'll take that vector U that I had there and just just have the 1, 2, 3. And let's see that this fails, right? So T of RU would be equal to T of, just 5 times U, right? 5 times this vector. So 5, 10, 15. And according to the rule for T, the resulting output would be 5 and then 150. Right? It's x1 and then x2 times x3. And then R times T of U, right, if I pull the scalar out, that would be 5 times, and then what is T of U? If I apply T to the vector 1, 2, 3, first component would be 1, second would be 6. Right? X1 and then the first component and then the product of the last two, 2 times 3. and multiplying this scalar by this vector, I'd get 530, which is clearly not the same as the vector I got before. So we're seeing that t of ru is not equal to r times t of u, for every vector in the domain u and every scalar r. All right. So as soon as you show that one of the properties fails, then it's not a matrix transformation, right, or not a linear transformation. That's not the other way around, though, right? Like here I showed one of those properties was true, but again, just because one of those properties is true doesn't mean that the transformation is a linear or a matrix transformation. You have to go through number 2 and number 3. You have to show both additivity and homogeneity. All right, so the answer to the second question, no, that is not true. So T is not linear, right, or not a matrix transformation. Again, those words are going to be interchangeable, really. Okay. So that means that if I went back up here, that means I cannot write this as some matrix times the original input vector. I can't do it. There's no way. All right, next one. Now, if, like I said earlier, right, if one of the properties that I showed you, one of those 4 properties, fails, then it's not a matrix transformation. All right. The only way you can show that it is a matrix transformation is to show that properties 2 and 3 hold, right? And show those properties of a linear transformation, the homogeneity and the additivity. All right, so look here. T is a transformation from R2 to R3. T of xy, right, from R2 is equal to x minus y, x plus 2. All right. So a two component vector gets mapped to a 3 component vector. And the question is, again, is T a matrix transformation or a linear transformation at that? Can I write this output as a matrix times the vector xy? Let's see what T of the 0 vector is. Now the 0 vector from the domain is the vector, 0, 0. That's from R2. And according to this, if I apply T to that, the first component be x again, so 0. Just replacing x with 0 and y with 0. Second component would be 0 minus 0, so 0. And the third component would be 0 plus 2. Uh-oh, that's not the 0 vector in R3. Okay, so like I said, just because that, we saw in the last example, if this property holds, it might be a matrix transformation. You really have to show these two. Okay, if you can show these two, then you're good, right? Then it is a matrix transformation or a linear transformation. But if any one of these fails, then you know for certain that it is not a linear transformation or a matrix transformation. Because if it were a matrix or linear transformation, all of these should be true. All right. So look, the first property is false. For this transformation, the 0 vector from the domain is not mapped to the 0 vector from R3, right? The 0 vector from R3 would be 0, 0, 0, not 0, 0, 2. So right away I can say, T is not a matrix transformation. Again, that's just because one of these fails. All right. But be careful. I'll say it one more time. I know I'm being repetitive. If one of these fails, it's not a matrix transformation. If you only show one of them is true, you can't say anything. You have to show these two are true, right? These are the big ones. Show these. Right? 2 and 3, the homogeneity and additivity. Show those to show that it is, you have to show both to show that it's a linear transformation. Just showing this or just showing that, just showing one of them isn't good enough. Right? But showing that one fails is good enough to say that it's not a matrix transformation. All right, and again, you could also look at the output and have told me that. Look at every term in the output. There's 1x, and then negative 1y. There's only a y in that. This term has x. Look at this last term, just positive 2. There is not just a single variable in that. There's no variables in that. I mentioned earlier, you're going to see in all these linear transformations between Euclidean spaces, R2, R3, R4, R5, whatever, that every term in each component of the output is going to have a single variable factor. Right? Which, again, this term right here does not. That threw everything off. So, and we saw here, right, so this output cannot be written as a matrix times the vector xy times the input vector. All right, great. And lastly, now again, I already did these kind of, this is just like the first two examples I went over. R2 to R2, again, t of xy equals 3x minus y, 5y, the first and second component of the output. Very easy to tell. Look at every term. 3x has one variable in it, negative y, one variable in it, 5y, one variable in it. This should be a linear transformation or a matrix transformation. Okay. Now you can either show the homogeneity or and additivity. You show both of those. Show that vector addition and scalar multiplication are preserved, both of them. Or if you see how to do it, and you can do it, write it as a matrix product, which we've done. I've done this before earlier in the video. This can be a 2 by 2 here, and down the first column the coefficients of x, 3 and 0. Down the second column the coefficients of y, negative 1 and 5, times the vector, the input vector xy. And you can double check, make sure that that's actually equal to that, and it is, right? So I can see how I can write this as a matrix transformation. So yes, T is a matrix and therefore linear transformation. It would satisfy that homogeneity property. It would satisfy that additivity property. The 0 vector here would go to the 0 vector here, and you can see that, right, when I plug in 0 for x, 0 for y. And also that fourth property where if I took the difference of two vectors, t of u minus v, it's equal to t of u minus t of v. And that's, again, all the properties you get, all the properties you can prove are true, all the things you can show are true in a linear transformation. You can start off with just the two properties of a linear transformation. You can start off with just the homogeneity and additivity properties. Wonderful. All right, so I hope that was clear about what I said about, just because one of the properties is true doesn't mean you have a matrix transformation. Right? So be careful with that. And yeah, hopefully it's not so bad. Hopefully it's not so hard to recognize when you do and when you don't have a linear transformation, when dealing with a transformation between Euclidean spaces, R2, R3, R4, and so on. Just look at all the terms of the output, right? That'll be a kind of a key, a dead giveaway. If all the terms of the outputs have a single variable factor in them, and not more than one or not less than one, right, variable in them, then you have a linear transformation or a matrix transformation. And if any of the terms you see has no variables or two variable factors or variables to higher powers, right? Because again, anything to a different power would be, if I said x to the half, that's half a variable factor technically. If I said x cubed, that's 3 variable factors technically, right? So all the powers and the variables are 1 as well. Then you'll recognize pretty quickly if you have a linear / matrix transformation or not. All right, so I hope you enjoy practicing problems of this nature, and thank you very much for watching.